hope you're on live too. All right, we're live.
All right. Well, today we've got a return visitor speaker that's been here before, so a lot of you know this gentleman and some of the people that's with him. Patrick Kiser is a construction engineer for Tennessee Valley Authority, and he knows what's going on out there. He's come to update us today. Patrick grew up in the Bristol, Tennessee area. Local boy done good, as we always say. Went to Sullivan East. Went to University of Tennessee, got both his undergraduate and his master's degree. So he's out there working on the dam, trying to keep the property owners at bay, and scuba diving, that kind of thing, I guess. So anyway, we're glad to have Patrick, and we'll turn it over to Patrick, and hopefully the speakers will.
Is this working? Thank you for having me back. It's been about 1.5 years since I was here. We've been working hard at Boone. We're on schedule. We're moving forward. And today I kind of want to bring you up to speed on where we're at and really talk more about where we're headed. The last time I was here, we talked a lot about really what our fundamental issues are and how we were going to mitigate them. At that time, we were in the middle of grouting, so we talked about grouting. So I'm going to touch on every piece of our remediation plan today, but I'm going to start back at the beginning and go through the background a little quickly just to kind of make sure everybody's on the same page. Before I get started, I wanted to thank you for introducing my colleagues here. There are a few of us that are out here speaking to public groups quite often, but there's a whole team of people that support everything that we do. Mr. Peterson is our quality manager. He's out there every day making sure everything's going right. Veronica has been our dam safety lead and overseeing the dam safety inspection program. She's transitioning into being our site construction engineering manager, working more with the engineering team. And Mel has been our community relations person. So without all these people working behind the scenes, we would not be near as far as we are today.
So that's why Mel got beat up, was because she's community relations.
Somebody twisted her arms.
Yeah.
So I want to say I've been with TVA for about 3.5 years. I came in about the time we started having problems at Boone. I am very passionate about what we're doing. I'm proud to be part of what we're doing. And I really do appreciate the opportunities for you all to come out here to ask us questions, hard questions, easy questions, because we want you to know where we are at. There is some nebulous features of the schedule purposefully, because if we tried to nail them down for you, we would just be making them up. And so we'll talk about that. We're specifically going to talk about the schedule today, and we'll hit that towards the end of the presentation. So before I get started, I just wanted to let everybody know TVA's 85th anniversary was May 18th of this year. And from the initial signing of the TVA Act, our mission has never changed. It's serving the people of the Valley. That's what we do every day. It's not a vision, it's not a goal, it's the vision. And although that mission has never changed, the way we deliver it to the people of the Valley has changed. We deliver low-cost energy, focus on protecting and being good stewards of the environment to preserve this for future generations, and just as importantly, economic development, bringing good jobs into the Valley. And our dam safety program is an important part of that. We support every piece of that mission. So today we're going to talk a little bit about the background, a little bit about the dam, its features, how it was built, what our fundamental problem is, what our remediation plan is. We're going to hit quickly on the drilling and grouting. I'm actually going to focus more, instead of what we were doing that I covered last time, but how we've taken that data and we've pushed that in to optimize our cutoff wall design. We're going to talk a little bit about the stability burns that we've recently completed, and then wrap up with the concrete cutoff wall and talk about the schedule and the upcoming work. Most people are familiar with the dam. We have a concrete and an earthen embankment section. The earthen embankment is about 900 feet long. The concrete section is about 850 feet long. The normal pool in the summer is 1,382 feet. The normal winter pool is 1,362 feet, and our tail race elevation's around 1,360 to 1,362, depending on when we're generating and how many units are running. So, normally we have about 100 to 120 feet of head, 120 feet of water behind the dam that's impounded in the reservoir. It's a typical earthen embankment section. Our seepage issues that we're dealing with are with the embankment section. The concrete section is stable. We don't have any seepage issues over there. This is a pretty typical embankment section for the time that this was designed and built. A lot of the Corps of Engineers facilities and other dam facilities were built with this same configuration at the same time. And as you are aware, the projects like Center Hill and Wolf Creek have been fighting the exact same issues that we are, and we're going to talk a little bit about that over the next couple of slides. The original designers of the dam understood what was going on at the dam, but this seepage and piping problem was not well understood in the industry. That's why you see it as a broad problem with dams these days. And it's the #2 cause of dam failures worldwide. And when I say #2 cause, it's in the 0.1% less than overtopping of dams. So it's a significant issue in the industry. So we have an earthen embankment section, and they understood that there were these pinnacles of bedrock underneath the dam that we're going to see in some of these pictures. But again, they didn't appreciate how that impacted the dam long term from a seepage and piping standpoint. They looked at it as more of a structural problem, and so we did a consolidation grouting program under the dam to essentially, in their mind, construct vertical columns to help support this load of the embankment. This is a earthen cutoff trench. So the idea was to excavate down to rock, cut off the seepage through the natural soils that were to remain under the dam, and serve as that seepage barrier. And then there was a concrete grout curtain drilled and grouted into rock. Very common design and construction practices for the day. So this is what it looked like before we built the dam. The concrete section spans the river here. It goes up this natural drainage swale and ties into this hill here. So all the seepage, all the land runoff, and all the seepage was directed towards the river at that time. And this is what the foundation looked like. You can see these large pinnacles of rock. You see the scale that we have men here. And their job there was to in this cutoff trench was to compact soil back under those overhangs. Right? There's just no way to get a piece of equipment in there to compact that material. In today's world, knowing what we know now, all of that would have been excavated so that you could get pieces of equipment in there to get a mechanical compaction versus this hand compaction that was the common construction practice at the time. This is a big pinnacle of rock. You can see back here in this part of the cutoff trench, they had gotten above those pinnacles and they're using equipment to compact material. But you can see as you come up the hill, we have these fins of rock that were still sticking out that they had to compact material around. And then here, you can see they're getting above the rock, and so you're getting into some normal construction practices that are like pretty much what you would see us doing today. So at the end, you can see we've got the lake impounded. You can still see some of the construction facilities, the switch yards in place, the control building, and the powerhouse. And so you have the reservoir that's impounded behind the dam, and it's constantly trying to seep under the dam through that earthen cutoff trench. But remember back to that historic photograph, all those drainage swales, surface swales, used to come back this direction too. And so not only do you have the seepage from the reservoir, you have the seepage from this high ground and these sinkholes up on the hills here that are also directed that direction. And so our flow paths, the hydrogeologic regime at the dam, is represented really by two sources. You have the reservoir, and these blue arrows represent seepage from the reservoir under the dam through the earthen cutoff trench, below the earthen cutoff trench. And then the red arrows represent surface infiltration. Water that falls to the ground, enters creeks, drops into sinkholes, and runs subsurface. So, as you can imagine, as we operated the reservoir over the last 62 years, we fluctuated it up and down. So during the summer, water level in the lake's high, everything wants to run downstream. Water level goes down in the wintertime, a lot of that water from the lake still tries to run downstream, but a lot of the water that's up in this high ground also wants to run upstream under the dam. So you kind of have this shifting of the water back and forth as we operate the reservoir. This is actually a video from the abutment. It's not under the dam, but this is physically what's been occurring over 62 years. We drilled a hole, we put a camera down on the ground, we turned the camera sideways, you can see water flowing, and those are pieces of soil. One piece of soil at a time. So 62 years later, we have a sinkhole in the parking lot at the downstream toe of the dam, and you have muddy discharge in the tail race. Now sinkholes aren't common, but they're not uncommon at dams. Infrastructure fails all the time. So you'll have old tow drains, you'll have storm drainage. I've responded to probably 100 sinkholes in my career. 90 of them have been associated with storm drains that have failed over time. Right? But when you get a combination of the sinkhole and the muddy discharge, it is an emergent situation. And that's why TVA made the prudent decision to lower the reservoir at the time and as quickly as they did. Here's some closer pictures for you help you understand just the scale. So this hole's doesn't look very big. It's about 5 feet this direction, 3 feet this direction. But over time, that hole never got bigger, but about a 40-foot diameter around this depressed. And so that's part of the early work that we did, was to come in and do some grouting and create structural columns around that sinkhole to keep it from impacting the control building and other infrastructure. Oh. I'm getting a little handsy here apparently. And then for some scale, there's a man standing in the picture up there. His name's Tim Boring. He's about 6'6", 300 pounds. So to put things in the scale, that's not a little muddy discharge. So as we've talked about in the past, our overall seepage remediation plan is build a concrete cutoff wall and grouting and berms. The reason we built a concrete cutoff wall is you know what you built, where we built it. It's a positive cutoff. It's a permanent cutoff in terms of deterioration. You essentially turn the embankment portion of the dam into a concrete dam. So from that point forward, the concrete barrier wall is the seepage barrier, and the embankment just serves to keep it stable. Well, because of modern design standards and the potential for future sinkholes upstream and downstream of the dam, because we can't impact the regional groundwater table, we've also added these stability berms, these rock berms upstream and downstream that are designed to keep the dam stable. If we have sinkholes anywhere near the toe of the dam, they're designed to collapse in and choke them off. And then the grouting is to provide more of a positive cutoff below the wall. Right, so you say, well, why don't you just build a cutoff wall to the bottom and not worry about grouting? Well, a couple things. You have to slow the water down so that you can build the cutoff wall in the first place. And secondly, it's just more economical. It's cheaper, it's faster than excavating all that rock and backfilling it with concrete. So it's really trying to balance and optimize the depth of your wall based on building it where you need it with some additional margin rather than building it full depth. So, when I was here in November 2016, we're in the middle of our drilling and grouting program. There were two components. There was a low mobility grouting program, which was done in the upper part of the rock, which was around these pinnacles. And that's really like injecting a brick mortar, something that's sandy. It's cement, water, and sand. It's made to push these soft soils out of the way, fill larger voids, fill larger cavities, displace the soils, these soft soils that are prone to erode. And then the high mobility program, which is injecting cement and water and other various components that vary in thickness from a milk to a milkshake, and its job is to penetrate the finer features in the rock and seal those up. So we worked about 14 months, 24 hours a day, 6 days a week, through all the weather. The only thing that really shut us down was lightning. We took Christmas Day off and the 4th of July and Memorial Day, major holidays, but other than that, it was an around-the-clock operation, and then Sundays were a lot of maintenance for equipment. In all, we drilled 539 low mobility grout holes, 276 high mobility grout holes, about 21 miles of drilling, and we put about 233 concrete trucks of grout into the ground below the dam. Every one of those holes we drilled was as much about collecting data and optimizing the depth of this cutoff wall as it was about getting the grout in the ground to serve the other purposes. We made direct observations of the material we recovered from the holes. We took pictures down the hole, developed 3D images of all of those to understand the rock structure and tie what we are seeing below the ground to what we're seeing above the ground to the rock outcrops. You can't see it here, but it's not showing up very well, but up on top, this is a hand plot of the geology. So we took every piece of data that we had, we plotted it by hand. We also used computers to help us sort through all of that and develop them and put them together. And this is a three-dimensional model of what we think the top of rock looks like below the dam. And so you can see some of these pinnacles. You can see the troughs between them. Here's the concrete dam, the control building. So this is kind of the basis that we developed for where to build the cutoff wall. How deep, how long. Moving to the next phase of work, these are stability berms. This is the original dam cross section. This in the yellowy brown color here is just kind of some common fill that we put in place to build the beach and things like that at the time of original construction. And so really we built a rock berm on the downstream side. This will also provide some room for the cutoff wall contractor to stage some equipment and some materials. And then on the upstream side, we built a larger rock berm. So the top width of our crest now is about 120 feet wide for most of the embankment. When we get into some pictures of the cutoff wall construction, you'll understand why. It's to help optimize their work and protect the workers. So this is what we looked like in construction back in the fall. This is the upstream side of the dam. You can see we're placing a bunch of rock on the upstream side. Here's what it looks like today. This was the sound wall that you could see in some of our grouting pictures. So the original crest of the dam is just on the other side of this wall. You see we've widened the crest of the dam a lot. There was about 160,000 tons of rock placed on the upstream side. On the downstream side, we built a graded filter, and here it is under construction back in the fall. This is what it looks like today. Here's the original crest of the dam. There's the sound wall we were just looking at. Like I said, from here to the upstream side of what we showed in the other pictures is about 120 feet wide now. And on the downstream side is about 60,000 tons of rock. My math isn't down to the exact ton. It was really about 223,000 tons of rock total. So our cutoff wall. We grouted down here. May or may not do any more grouting as part of wall construction, depending on the means and methods of the contractors and what we see as we go. But our goal is to build the cutoff wall through this portion of the bedrock that we cannot grout effectively to serve as a positive cutoff of the seepage. This is a three-dimensional model of the wall. So you can see here's the concrete dam. This is our top of rock profile. This is our concrete cutoff wall. And these are steps in the wall, and those steps go up and down to intersect specific flow paths and features that we've identified in the rock. So it sounds pretty simple. It's about, we want to build a wall that's 2 feet wide. It's up to 190 feet deep. So how do we actually do that? Well, we can't go out and just dig a ditch 190 feet deep, and blast through the rock. So it's very specialty equipment. There's contractors all over the world that can build cutoff walls. It's done every day for subway tunnels and stormwater tunnels and things like that. But very few people in the world have ever done it through a high hazard dam, just because the risks, the technical understanding of what you're doing, the focus on the public safety, and tied to the efficiency of the work is just a different level than what you would normally do for some of those other projects. So we build this in discrete elements, and each element is a distinct piece of work. And so we build an element here, we move over here, we build another element, and then we come back in between them and we build another one to tie them together. And essentially they consist of circular elements, so just drilling big columns, or rectangular elements, or a combination of the two. So we go in and we drill a circular hole through the soil, through the bedrock, to the bottom of the cutoff wall. We move a few feet away and we do it again. And we move a few feet away and we do it again. Those are called primary elements. The second element is we come back between them and we excavate all the soil between them and parts of those original primary elements to tie them together. We do that over and over, and we construct a wall that at its minimum dimension is 2 feet thick. Different contractors will do it different ways, different size elements, different spacings based on the risk, based on the geology, based on the hardness of the rock. Seems pretty simple in plan view here, but when you're trying to do it in three dimensions, you're trying to excavate hard rock. Part of your cutter equipment is in rock, part of it's in soil. As we try to penetrate these pinnacles, you're trying to maintain a tolerance for deflection so that you can tile these together and construct a continuous wall. It's very tedious in nature. Second method, we excavate rectangular panels. Let me back up a little bit. So those circular panels, they can be anywhere on the order from 3 feet to 6 or 7 feet in diameter. Right? They could be larger, they could be smaller. It's really tailored to the nature of the work in your site. These rectangular elements are generally on the order of 4 feet thick and 9 to 12 feet long. So again, we excavate one, pour it full of concrete. Move a few feet away, excavate another one, pour it full of concrete, come back and tie the two together. Or a combination. Primary elements are circular, secondary elements are rectangular. So our goal again is to build this wall that's 2 feet thick, but the wall is going to be bigger than that just to make sure that we get a minimum 2 feet thick, full depth, top to bottom, left to right. So this is cutoff wall construction at Wolf Creek Dam. This is why the top of our dam is 120 feet wide now. Lots of large cranes, lots of large equipment, lots of manual checks that have to be made by people working around it. This is Clearwater Dam in Missouri. They're excavating rectangular elements here. This is Center Hill Dam between Cookeville and Nashville, Tennessee. They're excavating rectangular elements there. Zooming in a little bit more. This is a reverse circulation drill. It's essentially a tunnel boring machine that's turned vertical. goes down through this casing, can cut pretty much any kind of rock out there. It's all a matter of just gravity and the types of cutter heads they use. This is used to excavate the bedrock portion. This is a hydromill or a cutter or a hydrophrase. These are the pieces of equipment that are used to excavate the rectangular elements. Now the piece everybody wants to talk about. This is our schedule. We discovered the sinkhole back in October 2014, lowered the reservoir shortly thereafter. We started grouting in December of 2015. We grouted until February of 2017. We've been constructing the berms, and this is where we are today. Our best estimate, based on benchmark projects, working with experts in the industry, is the cutoff wall and the testing that has to happen before we return the reservoir to normal operation will extend from this fall until mid-2022. So why the big time? Why the range, right? Seems pretty simple to build the wall, but it takes a lot of work to get to be able to build the wall. This is a industrial process, essentially. We have the width for the embankment build out there. The contractor's got to come in and build a work platform. It's a reinforced concrete structure to support their equipment, to support their means and methods, to maintain all of their fluids, to serve as an environmental barrier, to manage all the storm water, all the water and the fluids that come out of their excavations. We've got to build an on-site water and wastewater treatment plant to treat all of those fluids, to take the slurries that they will use and clean and treat them to be disposed of off-site. We've got slurry production and cleaning facilities, and this slurry is, as they drill these holes, excavate these holes, that's the fluid that's used to stabilize the hole, keep it open, keep it from collapsing, and carry those cuttings, those rock chips, those soil cuttings up out of the hole, runs through a processing system. It's cleaned out, reused. All that waste has to get treated, dried out, and taken off-site. We've got to build facilities to take those materials and then dry them out so that you can do something with them, pack them in place, take them to the landfill, whatever we end up doing with them. We have to customize an off-site batch plant. These are pretty highly specialized concrete mixes. It's similar to a drilled shaft concrete mix for deep placements. So if you're familiar with high performance concrete, ours is not quite as sophisticated as that, but it has to be a dedicated batch plant that's dedicated to the contractor 24 hours a day, 7 days a week. So whether they team with a local supplier, or they build their own on site, or they build their own at an existing batch plant, that has to happen. They've got to build just their on-site work areas, right? They've got to have equipment maintenance facilities. They've got to have offices and those kinds of things, right? And so that's about a year to 18 months to get that stuff built while they get their equipment here, get it erected, get it manufactured, delivered, shipped, erected, tested, and ready to start working on the technique area for the cutoff wall. So what are we going to be doing the rest of this year? If you go by the dam today, you'll see that we're cutting down the hillside behind our communications trailer. We, in communicating with the contractors during our procurement process, we got to see in general how they are going to use the site. So we're trying to get ahead of them and prepare areas for their use, so that way we can cut that out of their schedule once we're able to sign a contract. We're going to be installing additional instruments and automation equipment to monitor for dam safety during construction. There's a communications tower that's on the dam right now that supports part of our operations. That's got to come down this summer. Where we're tying into the concrete dam is immediately adjacent to our foundation gallery to the dam. So we've got to bulkhead part of that off and pour it full of concrete, so that way when we cut in and tie in with the cutoff wall, that we don't damage the gallery. And then as we move forward through the procurement process and we figure out what other things the contractor are gonna be doing, we're gonna start doing those ahead of us having that contract in place. So again, we can accelerate the schedule as much as we can and be ready as soon as we can for them to start productive work. And then this fall, once we select a contractor, they'll start their own engineering for their own utilities, their power, their water, their other infrastructure, and then the environmental permitting that they have to do. Dam safety is always our priority. The protection of the people downstream, protection of our workers, and quality. Those are our focus areas. We keep all those right, everything else falls in place. The dam safety is always our number one priority. Time for questions.
Yes, sir. You said that because of the sinkhole and the yellow blow off that you were in an emergency situation. What would have happened if nothing were done? And particularly to the dam, and what sort of time frame would that take place?
It's a potential emergency situation, and in dam safety world, you never know if it's actually going to develop. If that condition is going to develop into a dam safety situation. And there's not an exact science or an exact answer to your question. The sinkhole could have continued to progress and start impacting the dam. That could happen in a matter of minutes or hours. So I'd encourage everybody to go look at on YouTube and look up Teton Dam. They had flow through the abutment. So it wasn't underneath the dam, it was actually through the hillside where they tied in. One afternoon, they had a wet spot on the ground. By noon the next day, it failed and killed 43 people. So it's when you see those things, there's not an exact science for you to calculate it. It's at a point where every hour you delay making a decision, the risk goes up exponentially. And really, the only way to start impacting it is start loading the reservoir and start filling in the sinkhole. Yes, sir.
My next door neighbor has vegetation that is probably 15 to 18, maybe even 20 feet high, and who knows where it's going to be by the time 2020 rolls or 2022 rolls around. So, what does the TVA suggest be done? Because it's going to be a nightmare if no one does anything, and I'm just curious what the outlook is for that.
So I'm going to answer that in two pieces.
Can you repeat the question?
Yes. Okay. For those online that can hear the question, there are folks on the lake that have vegetation that's currently about 10, 15 feet high. Who knows what it's going to look like by the time we're done with the project, and what are our recommendations for management? So I'm going to answer that. I'm going to answer this in two pieces. Number one, we have vegetation management guidelines that we've worked with the TWRA to develop, and they're available online on our website. We have postcards on all the tables. For those online, if you go to this website here, you can access them there. That will tell you essentially what you can and cannot do in terms of managing that. From TVA's perspective, long term, if it impacts navigation, we will address it. Further than that,
We also have an internal.
yeah, we have an internal working group that's working on that plan. All right.
That's fine.
Is recreational boating navigation?
If it becomes something, not a hazard.
If it becomes I'm not a navigation expert, but that is actually, Mel, that's a question we should probably write.
Water skiing isn't considered navigation typically.
That's a public safety hazard.
Has the contractor to do the work for the cutoff wall, has it been secured? Has a contract been written for that scope of work?
We are in the procurement process as we speak. We expect to have the contract signed late summer, early fall.
just as an outsider looking in, I think that's part of the frustration.
Mhm.
If there is frustration here, maybe there is, maybe there isn't. But you knew, this cutoff wall has been part of the plan the whole time.
Mhm.
So it's just sort of puzzling to why that particular scope has not been secured before now.
Part of it is because of the optimization of design, but we've had these contractors working with us in constructability reviews. So it's not like we've handed them something they have not seen. They have been part of our design process and providing inputs so that we could optimize it and don't start off the project with re-engineering portions and slow it down any further. Yes, sir.
We've had an extraordinary amount of rain in the last month.
Yes, sir.
Has that impacted the workload or the scheduling of the work?
It didn't impact our work as much as it would have been had we been doing earth. Where we were dealing with rock, it was easier for us to deal with, particularly as we got up higher off of the ground with those burns. The work that we're doing today to grade at the site, it's shut it down.
Yeah.
It's hard to work with clay when it's really wet. As I was talking with this gentleman up here earlier, those of you that may be on Boone not on Boone, but on South Holster and Watauga may see higher water in those lakes these days because they're storing water so we can pass it through Boone and stay within our operating restriction. The fish shells you saw the other day, we were sluicing water while they were doing some maintenance work on the generators. Yeah.
So your cutoff wall, is that going through the area that you've grouted your excavating,
Yes.
your grout work? Okay, is there a projected life expectancy of this repair?
Our design life is on the order of 50, 60 years, but it's a concrete wall in the earth. It's not exposed to the elements, so, I expect it to be there for the functional life of the dam. I mean, this is a robust design as compared to others I've seen at the Corps of the Engineers. They had really big embankments. Wolf Creek and Center Hill, they were 250 feet tall. And so they had a really massive earthen embankment. And so ours was smaller. And so the berms that we built gives us additional margin to ensure the longevity of the structure as we intend it to function.
How about South Holster Dam? They expected to have the same issue then later on?
No, sir. They have different geology over there. And shortly after we had this issue here at Boone, as you can expect, we're always surveilling our dams. But every time something pops up that you don't expect, we went back and did what we call an extended condition evaluation, looked at all of our structures, particularly those that are founded on limestone bedrock. And as odd as it may seem, since limestone's around here everywhere, right underneath the embankment at South Holston is not limestone. Yes, sir.
If I recall, there were some issues with Center Hill when they started raising the water. They thought they had corrected some of the leaks and there might have been some seepage. I know that you were talking about raising Boone. I thought it was 5 feet because of lack of water. You maybe went 2 feet.
Yes.
So what can you tell us about the effort to see how the seepage has been dealt with?
That's essentially, so the last 2 falls, we've done the reservoir raises, right? A lot of the data that we've collected has been while the reservoir's been down, and so we're fluctuating the reservoirs to see how our instruments respond. So when we tried to do that last fall, we were kind of in the middle of the drought. We didn't want to pull water inadvertently or unnecessarily out of South Holston and Watauga to do it and impact water supply at other areas, and so we limited that to 2 feet. We may do a similar fluctuation this fall. It really depends on the contractor's schedule. We don't want to impede the contractor's schedule. But also part of what we're doing, the reason we're building the cutoff wall is we have a very complex flow regime here. All of our flow is not coming from the reservoir. We have something more similar to Center Hill. They also have a problem with water going around their dam. Well, we don't have water going around the dam. We have water coming back towards us from the outside too. And so that's part of the purpose for the cutoff wall and the berms to help support us raising it with more confidence. They've not raised Center Hill today. So the water level has been down, it's been up and down, but they're still not back to the normal operating pool at Center Hill.
How many years has that been now?
I've got a schedule here if you want to see it.
No.
It's,
That's been a
yeah.
long
It's,
time.
it's been a long time. Part of the reason theirs is still down is they have a saddle dam that's just adjacent to their main dam. And instead of building a cutoff wall through it, they decided to build a reinforced concrete stability berm just downstream from it, and it's under construction right now. So they're finding some additional issues there. Yes, sir.
Two-part question. First of all, next dam upstream on the problem would be the Willow Dam.
Yes, sir.
I suspect it's the oldest dam in this part of
Yeah,
the
it's one
PBA
over.
system.
Yeah.
And what is, I'm sure y'all looked at that. Is that,
Yes.
what is the situation with that? Because that would impact Boone again.
It's a concrete dam. So if you have a concrete dam and you get a sinkhole that comes underneath it, you may not be able to impound your reservoir, but you're very, 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 very low probability you're gonna fail a concrete structure. Okay? So again, if we had this problem over near our concrete dam, it's a concern, for sure. Anytime you get a sinkhole at the toe of your dam, it's a concern. It's the combination of the sinkhole, the muddy seepage, and then earthen embankment. We have time for one more question.
Hey, I saw they're changing out the generating equipment at South Holston.
Yes?
With Boone being down, does it need new generating equipment, or is it still operating?
We upgraded this generating equipment at Boone in the early 2000s, around 2010 timeframe, and those generators, when we upgrade them there, those are upgrades for like 50 years or things like that. South Holston's hadn't been upgraded since they were installed originally, and so the work going on there is really the first upgrade for those. That was one of the first questions we asked. Hey, while we have the reservoir down, do we know if we need to go in here and do a modification of our hydro units that had already been complete? Well, again, thank you for having me out today. Be more than happy to come back and let you know where we're at. If you ever have questions, mail's always at the trailer. You can submit questions through our website. Thank you.
Patrick, thank you for being here today, and we will expect you to come back and tell us how things are progressing at some point. Any more business to come before the club today?